This is the third part of the kinetics chapter that you need to have a knowledge of, and this is dealing with the integrated rate laws, which are related to the differential rate laws, and they give us another way to look at the data and talk about how the different rates are affected. The integrated rate law is different from the differential rate law, and it gives us another way to look at the data and determine the order, but this time we spend most of our time looking at it graphically instead of algebraically. This expresses how concentrations depend on time, and it depends on the order of the reaction. Remember that the differential rate law says the rate is equal to a constant times the concentration of the different reactants to their order. Overall order for the reaction is n plus m. The integrated rate law takes the form by integrating the rate function. And so when you integrate, you're taking the area below the curve. So instead of focusing how rate changes with concentration, we are figuring out how concentration depends on time. The value in n and m change the order of the reaction. The form of the integrated rate depends on the value of n. You get a different equation for 0, first, and second order equations. So what we have to do with the integrated rate law is we need to focus on just one reactant. And the way we do that is by making all the other reactants have extremely large concentrations so that their rate doesn't have a major effect on the reaction. So order of the reaction determines or affects their calculations. When you have a zero order reaction, it means that the concentration of the reactants is really insignificant, and you get this when you are dealing with a catalyst or an enzyme. And in that situation, the surface area of the catalyst is the rate determining factor. So it doesn't show up as the change in concentration of any reactants having an effect. First or second order is more typical of what we see and more typical of college problems where the amount of reactant does make a difference. So to look at the integrated rate law for a zero order reaction, we know that rate is equal to K for a zero order reaction, because the concentration of the reactants all have zero order, so they don't show up in the differential rate law. And rate is equal to the change in concentration of our reactant with respect to time. It's always a negative because our reactant is always going down in concentration, so that's why the slope is always negative. And so what we can do is we can set up a differential equation where we take the change in A and put it on one side of the equation, and the change in T and put it on the other side of the equation, and that's how we get dA equals minus K dt. So we move the negative sign over to the right side as well. Since both of those sides, the concentration and the time, both have 1 in front, when we integrate 1 with respect to A, that means that we just get the concentration of A. When we look at a first order reaction now, A is part of our differential rate law, so now we get that the rate, or the change in concentration of A with respect to time, is equal to K times the concentration of A to the nth power, and since n is 1, we can integrate this. We get a new form for the equation where we get the natural log of A equals minus KT plus natural log of A naught, where A naught is the initial concentration. So now as your concentration changes, it's going to show you what your final concentration will be based on your initial concentration and what time you have allowed the reaction to run. The reason why this works, again, is if you set up the differential equation, you have dA equals minus K dt, but now we also have that concentration A on the right side, so when we move that to the left side, it ends up being on the bottom. So what we're really doing now is we're integrating 1 over the concentration of A with respect to A, and when you integrate 1 over A, that works out to be the natural log of A. I know that a lot of you have not had calculus already, and those of you that are in calculus may not have seen any integrals, so this will make a lot more sense later on. You really don't need to know the math behind it. I just like to show it so that you have an understanding when you do see it of where this all comes from, and also because since some of you do have or have done integrals to this point, you can follow along and seem to get a better grasp of where all this comes from. So here's the first order integrated rate law. The equation shows that the concentration does depend on time. If you know the K value, or your constant value and your initial concentration, you can calculate the concentration at any time. And that's why this becomes a powerful equation to use. It's in the form of y equals mx plus b, where y is the natural log of a and the slope is minus k, and b, the y-intercept, is the natural log of your initial concentration. You can also rewrite it as the natural log of a naught over a equals kt, and you can just manipulate that mathematically. Again, if you need to see this, I will go through all of this step by step in class. But this equation is only good for first order reactions. And so here we can see that the pressure with respect to time has a curve to it, but what we're trying to do is we're trying to linearize this graph, and that's why the natural log is used, because when we take the natural log of the pressure, you can see on the right now that that is a straight line, and that shows us, now that that's linear, that this is a first order reaction. If the first one was a straight line, then we would have known that it was a zeroth order reaction if the one on the left was a straight line. So here's a reaction where we could look at the data that we got from an experiment, and as time goes on you can see that the concentration is changing. We can see if it's zeroth order, first order, or second order by looking at this. So the three columns are going to give us the order. So if there's a constant change in any of those columns that's constant throughout the whole time, then we know that order is correct, because that would mean that it's a linear graph. So if we look at the concentration of the nitrogen dioxide by itself, meaning a zeroth order reaction, we can see that that concentration does not go down by a constant amount, especially when you notice that the time goes from 100 to 200 to 300, and the amount that our concentration is changing is actually decreasing in the difference between those data points. So it's definitely not zeroth order. So then we look at the natural log column to see if it's first order, and we can see that it's somewhat going down by a constant amount, but again the time isn't constant in this chart. It goes from 0 to 50 to 100 to 200, 300. So that means that the natural log of nitrogen dioxide is also slowing down in its change. So when we go to the third column, we see that there's a 27 difference between 0 and 50 seconds. There's another 27 difference between 50 and 100 seconds, and then there's a 54 difference between 100 and 200 seconds. You could see that that would be a linear graph, and therefore this is a second order reaction. So there's the first order on the left, and there's what the second order looks like on the right. And if you're wondering why that has an increasing slope, again, I can go through that math in class and you can see where the negative sign ends up. So if you see just graphing concentration versus time, if it turns out to be a straight line, then it's a zero order reaction because the concentration does not change how the rate will be changing. But if it has a curve to it, it's going to be a first order or a second order. So here's what all the rate laws look like, where you have 0, first, and second order. And the differential rate law is in the first row. The second row then has the integrated rate laws, which you need to know all three of those. And then your linear graph is going to have the two axes that are listed there, where the zeroth order is going to be the concentration of A versus time. The first order is going to be the natural log of the concentration of A versus time. And the second order is going to be 1 over the concentration of A versus time. The slope for 0 and first order is negative, second order is positive. And then the last part of this is that we can calculate a half-life. And the way you do that is you put in a value of 1 for your initial concentration and 1/2 for your final concentration, and then you can solve for the amount of time it would take for you to get from 1 to 1/2. And I can go through that math as well in class. I'm not going to go through that here, but I can do that on the board while we discuss it. And you can see what the equation is for the half-life for 0, first, and second order. The first order is the most common one we deal with. So here is a reaction, and you have this data. And so again, you can compare and see what the data looks like for 1 over and a natural log to see if it's second order or first order. And when you graph it, you can see that the natural log is curved. 1 over the concentration is linear, so again it's second order. All right, so in order to derive the reaction order, you can plot all of your data versus time. You can choose the straight line, y equals mx plus b, and so when you try the 3 different equations, you will figure out what order it is, and that's how we will do it in the lab. And then we can get the K value by calculating the slope. As I said earlier, you can find a half-life for all of the different reactions, the amount of time it takes half of the reactant to be consumed. This can be determined graphically, or you can also calculate it from the integrated rate law. And so here's the graphical determination of half-life. So you can just pick 2 values and see where 50% occurs and how much time it takes. And you'll notice that the half-life is going to be the same amount of time all the time. So you should be able to see that repeating number over and over and over again as you keep cutting your concentration by 2 or 4 or 6 or 8, on and on and on. So again, here are the 3 half-life equations for the 0, 1st, and 2nd order rate law. The most common one that comes up is when we're talking about half-lives of radioisotopes. The decay of radioisotopes is a first order reaction, so that is the half-life equation for a first order reaction, which is the T1/2 equals 0.693 over K. You might have seen that number in math at one point, and we can also use now the integrated rate law in one of its forms to calculate the amount of and radioisotope remaining after a certain amount of time based on its half-life. So we will go through calculations like that. And that concludes all of the VODcasts on kinetics. The rest of the stuff we will practice and discuss in more detail in class.